I'll say slightly less menacing things as we go on. Dear Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this class, Lord, and just help us to understand a little bit more about power series calculation and also a little bit more about infinity, Lord. In your name I pray. Amen. Okay, so the time has come for me to talk a little bit more about the, well, to take a topological perspective, this is the one-point compactification one-point compactification of the complex plane. Now, let me draw a picture. The basic idea is to trade the complex plane, all right? And so what you can imagine is sitting a sphere, all right? And there's a couple different ways to set it up. For the purpose of my illustration right now, I'm going to set up the south pole of the sphere at the origin. All right? So the south pole of the sphere is connected to the origin on the complex plane. All right? And I'm envisioning this sphere, unit sphere for the sake of discussion here, to be just resting at the origin. All right? Then the idea is that we can make the north pole of this sphere basically be infinity. Right? Now, and then there's a one-to-one correspondence between this sphere and the the extended complex plane. So the picture is something like this. You draw the north pole, all right, and I'm going to draw it dotted until it leaves the sphere. That's the point at which it leaves the sphere. And then this goes down to some point in the complex plane. All right? Or let me draw on the other side another such picture. You can imagine the line starts at the north pole, leaves this and exits the sphere, and then intersects the complex plane down here. Right? Let's see here. What would happen if we, say, had a point, had a line which went, it could do this like that. I mean, I guess technically speaking, oh man, this is not what I want. I'm going to have to call an audible here, to use some sports lingo. Not that I'd really know, but let's put the south half of the sphere under the complex plane, and I think I'd rather have the equator on the complex plane. So if you can imagine this actually being on the complex plane, right? So the south pole would no longer be on the complex plane. It would be, let's see here, if the center, if this is the origin, right, in here, right, then the south pole, and if the origin is, say, 0, 0, 0, then the south pole would be 0, 0, minus 1. The north pole would be 0, 0, 1. If you understand my system of coordinates, so z is up and down, and the complex plane is the xy plane. The intersection of the sphere and the complex plane, as poorly drawn by me right now, is the unit circle. All right? So let me just try this picture one more time. So I'll start with the sphere, all right? And then you've got the complex plane. You know what? I give up. I can't draw this thing worth anything. I give up. I give up. You got to know when to fold. Okay, so I did want to draw one more thing on my previous slightly wrong picture, slightly distorted picture, which is if we had a line going from the North Pole right inside the sphere. So suppose it's still inside the sphere. I'm going to stop with the dotting. I don't know if you can understand it. So that point intersects the complex plane right there, right? And then it would intersect the sphere like that. Let's see here. Maybe I should just use two different letters. So let's say that this is Z prime, this is Z. This is W prime, this is W. Oh, oops, wait, other way around. That's W, this is W prime. Over here, let's say that this point is Y prime, and this over here is Y. So what I'm trying to indicate here is that, you know, Y, Z, and the W, these are in the complex plane, whereas, you know, Y prime, Z prime, W prime, these are all in the sphere. Let's call that, what do you want to call the sphere? Let's call it S2. All right, 2-sphere. So despite my poor artistry, can you, well, let me, hey, you know what? I know a way we can make this more precise. How about this? What if I draw the picture like this? Here's the complex plane, right? And let's just look at a cross section. I can draw circles better than I can draw spheres, right? So what's the, like this, right? So up here is your North Pole, down here is your South Pole, right? And then there's basically two different kinds of cases. The one case is that you've got a line which, so here's my, you know, Z prime, here's my Z. The other kind of case, I would say, is like this, right? So here's my W, and here's my W prime. The stereographic projection. What is stereographic projection? It's the map, depending on, I suppose if we, it would be the map Z prime maps to Z. All right. So stereographic projection, what does it do? It takes the sphere, right, and it maps it down onto the complex plane. Now, what can we say about this map? I mean, it's 1-to-1 is one thing you can see if you analyze this map. I could actually, if I was better prepared, write formulas, explicit formulas between this. I mean, you don't just have to give a picture. What happened? Something crashed and broke. It was a metaphor for this lecture. I mean, I don't know. It's like, all right, let's hope not. Let's hope not. Let's hope. There's still hope. There's still hope. So Z prime maps to Z. That's the stereographic projection. It's taking the sphere and mapping it onto the complex plane in such a way that what? Like you're mapping the whole southern. I mean, there's the other stereographic projection, and maybe this is not the standard one actually, but the other one would be to, it could use the same kind of idea and rest the sphere on the plane. There's two different ways to set this up, and that's one of the things that's bothering me. But the larger point here is this gives us a 1-to-1 correspondence. So in particular, you can think of the extended complex plane as this particular sphere under this correspondence. And more than that, you can even, the mapping, when you study it, you can make that mapping conformal in the sense that it preserves the angles between vectors on the thing. However, that's not conformal. I do not believe it's conformal with respect to the usual geometry of the sphere. It's conformal with respect to a kind of weird geometry of the sphere. In other words, really you're forcing the sphere's geometry to be conformal by just lifting the metric on the plane up to the sphere in a sense. Now, I don't think those words make a lot of sense to you guys, and that's okay. I'll try to write a homework problem which makes these ideas more clear, all right? But what I can show you today is a picture of what I'm saying. We'll see if it works. So this is a picture. What this is like a little sphere where the grid, so what the idea is here, is under this mapping, you're taking a grid on the complex plane, right? And then taking that grid and sending it through the stereographic projection, or possibly the other one that rests the sphere on the plane, because that's the bad part of my lecture today. But it's taking that grid and through the stereographic projection, just wrapping it around the sphere. And so this would be a set of perpendicular lines on the sphere with respect to that non-standard notion of distance on the sphere. So to give a notion of distance and angle to a curved space, we put what's called a metric on it. Now let me see if I can get this thing to work. I'll turn off the lights here for a second. If I'm lucky, I can get it to work. Yeah, both of them. Thank you. All right. So hopefully this will show up. We'll find out soon. So what's happening here is that the light source is serving as essentially the North Pole, right? And so light rays from this essentially point source of light are shining from the North Pole to the points on the sphere, and then of course the grid on the sphere is blocking out what's apparently a rectangular grid, right? So admittedly, my setup is wrong, and I am now sure that the North Pole is resting at the, well, oh wait a minute, I'm an idiot. I'm sorry, I'm still wrestling with whether or not my initial picture was right, so ignore that. But you can see it anyway, right? Isn't that neat? So this is the stereographic projection and the the transference of a seemingly curved grid to actually a square grid. And you see the conformality, right? There's 90 degrees on the board. Well, these are 90 degrees. Well, oops, these are 90 degrees. Let me turn the light back on. Thanks. This way it's one of my favorite toys. So, all right. Getting to the point here. So we can talk about the extended complex plane, right? C union infinity. And depending on what kind of question you want to ask, you could either think about that in terms of the sphere model, right? Or you can just explicitly think about it in terms of equations. Here's the equations to think about it, all right? So what would we mean by like the limit as z goes to infinity of f of z? How would that be defined? I think I told you guys this before, but it's time to revisit it. I've yet to test on this, right? So what we do in terms of algebra is we replace this with a limit as w goes to 0 of f of 1 over w. You could actually look at, on this picture, it's kind of neat, because if you look at this picture, you can imagine like a little disk around the North Pole. If you imagine like a little open disk around the North Pole, and imagine what that would look like under the stereographic projection, what would it be? It'd be like like an exterior annulus, right? So the neighborhoods of infinity, a disk of, let's say, radius epsilon centered at infinity would be what? It would be something like, z in the complex plane such that what? Such that the modulus of 1 over z is less than epsilon, I believe. Which is to say what? I mean, we could restate that. This would actually mean what? That the modulus of z is what? Greater than 1 over epsilon, something like that. Yeah. Okay, so that's the basic idea is that if we want to think about things at infinity, we replace z with 1 over z. So if I want to find a power series centered at infinity, what would that mean? What would a power series centered at infinity look like? So what you want is something like this: f of z equals to, and this is a slight abuse of notation at the moment, of course. I'll get back to my notes here momentarily, and we'll try to be more careful. But essentially, this is the idea. Because if that's the formula for f, what happens if we retrade z for 1 over w? What happens? This says, you know, g of w equal to f of 1 over w is what? What happens? We put 1 over w is just w to the n, right? So the point is, to work with infinity, we think about taking something we know and replacing z with 1 over z. That gives me the corresponding object at infinity. That's the idea. So a function which has well, it's not technically, it's not a power series expansion, right? But if a function has this kind of expansion, right, in some sort of exterior annulus, then we think of such a function as being holomorphic at infinity.
Is there a reason that we don't generally apply this concept to the real numbers by adding the point in the graphical line rather than the circle?
That's a good question. Why don't we look at the one-point compactification of the real numbers more? I suppose it's that a lot of applications of the real numbers, the ordering of the real numbers is important. So maybe it's more natural to think about the really long line where you've adjoined an infinity and a minus infinity, which we think is disparate and is distinct, yeah? And so if I was to identify both ends of the real line, I would lose ordering, right? That definitely violates the ordering of the reals. And so, but I'm sure there are other reasons in places where we do use it. Oops, I think I may have just erased part of the board with my shirt. So to give you an example, this guy, f of z equals to sine of z. Remember, this is what? The sum n equals 0 to infinity of, like, you know, minus 1 to the n, z to the 2n plus 1 over 2n plus 1 factorial. This would not be holomorphic at infinity. Like, this is an example of something that's not you know, holomorphic at infinity. In contrast, if we looked at, say, g of z equal to 1 over 1 minus z, all right, is that holomorphic at infinity? I'm not sure right offhand. My suspicion is, well, let's make it simpler. How about this? 1 over z plus 1 over z squared. Is this holomorphic at infinity? Well, you know, if we look at, I need the corresponding, maybe I should have called this f. Let me call this f so that I'm in concert with my language over here. G of w equals to f of 1 over w is what? Which is what? W plus w squared, right? And so that's a power series. I mean, it's a polynomial, and hence that's holomorphic, right? So then that means that 1 over z plus 1 over z squared is holomorphic at infinity. To be more precise, this is our definition, to be more clear. Definition, f is holomorphic at infinity if, let me use the slightly, say f of z is holomorphic at infinity if f of 1 over z is holomorphic where? Zero, right? This is the idea. What does it mean to be holomorphic at 0? It means that there exists an little open disk around there on which the function's complex differentiable, right? Or as we've learned more recently, if you can find a power series expansion for it, right? On some open disk, then that is holomorphic. So in other words, analytic if and only if holomorphic on a disk, right? We have that. Okay. So my apologies. I'm still up in the air. There's something not clarified in my mind yet about whether or not I want to look at the circle that's centered like this or the circle that's resting on the complex plane and why we would use one or the other. I've seen both in books. They're both used, okay? There's a reason for using one and not the other, and I'd like to clarify that for myself. It's something that's always vexing to me, and I run out of time and forget to explain this to students, and it's bothering me. One thing. But I hope, setting that aside, that this has given you some better sense of what we mean or what we can mean by infinity and how we deal with infinity. Let's see if I have something more to offer us in the notes. I think I should. Careful not to look at the test for later today. We want to do that. Just give me a second here, make sure I hide away any, Prove the orbit stabilizer theorem. Let's see here. See, now, does that mean now for sure that it's not on the test, or does that mean for sure that it's on the test? These are the questions you have to ask yourself, right? If I say something like that, now what could we justifiably glean from that? If I say that something's on the test at this point,
probably nothing.
I think
If you just say it could be or it could not be.
so you think it's essentially meaningless. Okay. The Battle of Wits. What's that? Am I what? I missed it, Sam. Sam's like, inconceivable. Let's see here. All right. All right, so let me just make sure I haven't butchered some definition for a second. Is okay? Or are you just zooming out? Excellent. All right, so what's my, so my entering comment here is that to study f of z at infinity, we study the corresponding function g of w is equal to f of 1 over w near 0. That's the guiding principle here, is whatever is true for the function composed with the reciprocal at 0, we say that is the behavior of the function at infinity. That's essentially the definition. But it is actually a natural definition if you filter through this model over here and how it interplays. So it's analytic at infinity if f of 1 over w is analytic at w equals 0. Analytic at something is equivalent to saying holomorphic at something, all right? Because analytic would just mean that there exists a power series, right? Now, so here's a little bit more. So there exist coefficients, b1, b0, and a row greater than 0 such that this is convergent, right, for all w meeting, within row a distance from 0. So by theorem 10.5.2, we have that this converges normally, right, on the open disk of convergence. But if you look at that, if z is greater than 1 over rho, then that means that 1 over z is less than rho, which means that we have this converges normally on the open exterior annulus of inner radius rho. Well, 1 over rho, rather. So that's an exterior domain with radius 1 over rho. All right, anyway, it's pretty neat. A couple of important examples. Things that are very nice at 0 are not nice at infinity. Like sine is not nice at infinity. A polynomial is not nice at infinity. See, because this, while is, yay, it's, definitely holomorphic at 0, but the reciprocal, the g of w here, if you, replace z with 1 over w, you got a sum of things that are divergent, right? This is not analytic at w equal to 0. So polynomials, in some sense, are not behaving nicely at infinity. And on the other hand, things that misbehave at the origin behave at infinity. There's this sort of... And of course, then, more generally speaking, you have things which misbehave both places. Right? You can have something that's got what we'll later call a pole at the origin, but also has a pole at infinity. These ideas we want to make more precise in the next couple weeks. All right. We'll be talking about Laurent series before long. A Laurent series is an extension of power series which has both has positive power terms and some negative power terms, finitely many negative power terms, or the so-called singular part of the Laurent expansion. Anyway, we'll get back to that. Here's an example. Z squared over z squared minus 1. If we look at the 1 over w, we get this, which gives us that. But then that, by the geometric series, is this, right? So, lo and behold, this guy is holomorphic, or as I'm saying here, analytic at infinity. All right, enough of this. You guys get the idea? I think. Let's go on. So section 10.7, we have to talk about for the rest of today is on the manipulation of power series. So a lot of what I'm saying here is that we can still do the calculations we were doing in calculus 2. All right. So what's my first theorem? If we have a pair of convergent power series, right, on some domain D, then we can take a complex linear combination of them, and supposing, of course, that we have the summation structure matches up, right? These are both k powers, and the sum is starting at the same point, right? They have to match up. If we had different starting points, or if we had different looking labels there, we'd have to do this kind of stuff. If you've had differential equations and worked out series solutions, you know what I'm talking about. You have to add matching things, right? These are already matching, so it allows us to add the coefficients to the series just like that, right? So what's the proof? The proof is, well, we have f and g analytic on D, which means we get that, right? And I define h to be the linear combination of f and g with the constant c there. And I just calculate the derivative. I mean, first of all, I know that this is differentiable because it's the sum of complex differentiable functions. And, right, I mean, the fact that h exists and is infinitely many times complex differentiable follows immediately from the fact that f and g as given both exist and are infinitely many times complex differentiable since they're holomorphic on this domain, right? Well, anyway, so I calculate the kth derivative of h, and by properties of complex differentiation, I get this, right? But then remember the Taylor's coefficient for f, the Taylor coefficient for g is this and this. But on the other hand, we know that the Taylor, the kth derivative divided by k factorial is this guy, right? And the kth derivative of g divided by k factorial is that guy. So that's a sub k, that's b sub k, and there you have it. That's the kth coefficient of the power series expansion for h, and the theorem follows. So I don't know. I think it's a nice proof. next I should tell you about the Cauchy product. What's the Cauchy product? If we want to multiply two series, there's a question as to how exactly are you doing that? Because if you're multiplying infinitely many things, if you arrange those things in different ways, in principle, you could change the outcome of the sum. That actually won't happen for us in our context because we have what's called, we have complex series are nice. That won't happen for power series, but you got to be careful. I mean, there's, what I'm trying to remind you of is Riemann's rearrangement lemma, that if we have a conditionally convergent real series, we can rearrange terms to get any real value. On the other hand, if we have an absolutely convergent real series, then we don't have this problem. We can rearrange the terms in the series. It doesn't change the limit. It doesn't change the sum of the series if we have absolute convergence. But anyway, we should define the product. Here I do. So this times that is defined to be sum k equals infinity ck z minus z naught to the k, where these c sub k's are produced by doing what? Taking the sum n equals 0 to k of an times kn minus 1. So all this is really saying is you just multiply the series by going order by order by order by order by order in the way that we always do. But this is a careful definition of what we mean by the product of two series. And then we can prove that, in fact, if we do have two convergent power series, this guy and that guy, and we form the Cauchy product from these two, then this is likewise convergent. And, in fact, it is also convergent on what? Where is it convergent? I'm saying it's still convergent on the same disk, right? I'm not saying anything more about whether or not it may be convergent on a larger disk. It might be, right? For example, if you take the power series of a function, right, and you take the power series of the reciprocal of that function, and you multiply them, what happens? You get 1. What's the radius of convergence for the constant function 1? I mean, the constant function 1 is an entire function. It has radius of convergence infinity. It's possible to multiply two functions in such a way that you get a larger radius of convergence for the product. That doesn't have to happen. This is just guaranteeing it. At least it still converges on the same disk. So here's the proof. Let's look through it. So we have F, N, and also G with this power series, right? That means that they're both holomorphic on D, so their product is holomorphic, right? And we have the product rule, right? Then theorem 10.5.2 shows that FG is analytic at Z naught, hence there exists. So what is this theorem 10.5.2? Let me click on it for a second here. What is that theorem? Ah, it's the one we proved last time, right? What did that theorem say? It said that if it's holomorphic, right, then it's what? It's analytic. What have I done? Can I? Well, kind of. Kind of. Kind of not. Kind of not. Yeah, that's, if I have any complaint about my current PDF viewer, it's that. Okay, anyway. I hope you guys remember the theorem numbers because I'm not clicking on any more of them. So the, in other words, because this shows that the product of the functions is complex differentiable or holomorphic, right? Then the theorem implies that it's analytic in the sense that it has a complex power series expansion, right? So since it's analytic, that means that there exists some constants such that ck z minus z naught to the k models the function, right? And then all that remains to show is that this c sub k is actually given by the Cauchy product, right? We know c sub k exists. Now we just have to show it matches the Cauchy product. That will prove the theorem that we're trying to prove. And to show that c sub k matches the Cauchy product, it's a simple matter of just differentiating in looking at the Taylor coefficients again. So we just need to show that the kth derivative of h evaluated at k factorial is equal to the Cauchy product. So start out at 0th order. Evaluate h at 0. What you got? You got f of z naught times g of z naught, which is, by the way, a naught b naught. And that, in fact, is the 0th term in the Cauchy product expansion. What's C1? Well, C1 is defined to be A0, A1 B0 plus A0 B1. Again, that's what we get from differentiating h prime. So it matches. How about the second term? Well, the second term in the Cauchy product looks like this. 2A2B naught plus 2A21, 2A1B1 plus 2A... I don't think that something is amiss here. What's this? Is that right? That doesn't feel right.
You have 4 terms.
I think that... I think these twos are bogus. These twos do not belong.
You differentiate twice, and you have a 2 and the denominator.
Yeah, but, oh, what's that?
That double prime is 2 times the coefficient.
Yeah, okay, then I must need, I don't, it feels wrong to me for some reason. What is C2 equal to? So C2 is the sum n equals 0 to 2 of a sub n, b sub, 2 minus n. So that's going to have A0, A0, B2, A1, B1 plus, oh, okay, it is, I'm an idiot. So it is literally just, I'm a dummy. You guys got it. You're like, what's wrong with you? Well, we know many things, but A0, B2 plus A1, B1. I'm sorry, I'm trying to imagine some sort of combinatorial weighting for this Cauchy product, which is dumb. It's not there. It's just that. That is C2. So we had twice that in what I was just looking at, which should have comforted me, if not for my ignorance. So yay. So this is twice that, which is what we want, because h prime prime divided by 2 should be c sub 2. And then, I don't know if you knew this or not, but this is Leibniz's kth power rule. So this is, if you want to take the kth derivative of a product of functions, in fact, this is a known formula. You can prove this with induction or something. Actually, the value of the derivative is you take the sum over I plus j equal to k factorial over I factorial, j factorial, the ith derivative of f, the jth derivative. This is actually true in the real case as well. This is not a complex thing. This is just a calculus thing. It's the extension of just the regular power rule. If you keep taking power rules and look at the combinatorics of it, this is what pops out. And so when you look at that, that's exactly, if you evaluate it, of course this divided by z naught is exactly ai, and that's bj. So this is ai, that's bj. Although I've eaten up the factorials, I'm just left with k factorial ai bj, but that's exactly k factorial ck, which then we divide by problem bumping into things lately. So there you go. That's the theorem, because we've just showed that the kth derivative of the product matches the kth term in the Cauchy product. I like this proof because it's, well, it's really just heavily computational, right? I mean, it's not, we do this stuff, oh, uniform convergence and this slick and that slick topological idea, and then there's this proof, which is just like gory calculation. I love it.
So could you come up with this from an intuitive perspective of rearranging series and then give it another rating by the same result? That seems like it would be a really interesting way of thinking about the product rule in general.
I don't know. I can tell you this, even for real series, when we satisfy the ratio test, right, that gives us absolute convergence of the series. So it's always the case on the open interval of convergence for a real series, we actually have absolute convergence. So power series are also in some sense normally convergent in the real case. And anyway, absolute convergence allows us to rearrange the terms, and that freedom to rearrange terms in some sense means that when you multiply series, you can't mess it up by multiplying them in kind of different ways. It's also true that if you have the Cauchy product also exists if you just have one absolutely convergent and one convergent series. Like it's enough to have one of the series involved being convergent. The product still is defined and the Cauchy product still works. This is
Just think of it as like
true.
you're just multiplying them out and you just pick all the ones given orders.
Yeah, yeah. In fact, that still makes sense over in algebra. It's in my paper. I think it's actually even true for non-commutative algebras, but whatever. Let's get back to the calculation. So how about here? Find the power series to order 5. What we have for the last 5 minutes of class should be relaxing. So how would you find the power series for sine z, cosine z? I mean, one way you could do it, this would be the stupid way to do it, but it's a way we could do it, is to, okay, power series for sine, power series for cosine. We do the Cauchy product, right? Look for, term by term, add things up to order first, the next order up is 3, the next order up is 5, right? And then, of course, that's 2z, and you do the math, 4/3 and 4/15. But what would the much smarter way to do this one be? What you didn't know in Calculus 1 can still hurt you here. So, 2 sine z cosine z is sine 2z. So that's like way, way easier, right? See? Or just make a substitution. So z minus 1 over 3 factorial quantity cubed plus 1 over factorial quantity to the 5th, but that gives you 32 over 120, which is 4/15. And this gives you 8 over 6, which is 4/3. And of course, that's 2. So, yeah, we could do Cauchy product, but yep.
What was the general response to the rearrangement lemma? Because it seems kind of paradoxical. Why is it not paradoxical?
Oh, it's not paradoxical because rearrangement of a series is not something you can do. You can't just rearrange series willy-nilly and expect the result not to change. That's the that's the thing that's wrong. I mean, we can start out with something like, I mean, here's a more ridiculous example of that, right? And then say, oh, well, I'll do, I'll do 1 minus a minus 1, right? And then minus 1 minus 1, and then, rather, just regroup them like that. I'm just rearranging the sum, right? I'm just saying add those two, like those pairs first, right? And so this is 0, and that's 0, and that's 0, and that's 0 forever and ever. And so that's 1. 0 equals 1. Yeah, there you go.
Our series is this form generally just kind of thrown out, not considered, or are they just considered in that context?
We can consider conditionally convergent series. We just can't rearrange them and hope that they remain equal.
Okay.
So, for example, to give you a more specific example of that, if I have the sum, n equals 1 to infinity of minus 1 to the n plus 1 over n, that converges to the natural log of 2. This is the alternating harmonic series. If I start regrouping terms in that, it won't converge to the natural log of 2 anymore, and it's technically a different series. So really, the larger point is conditionally convergent series. It's not just the terms which are being added, it's the order and grouping in which they're being added. For an absolutely convergent series, it's enough to just tell me the terms. It doesn't matter which way you add them, you're still going to get the same result. Yeah, that's the rearrangement theorem. All right.
So that comes out when you think of it as a sequence of partial sums rather than as an infinite sum of terms.
Yeah, well, the proof of these things has to be given in terms of like sequences of partial sums and such. Yeah. Right. All right, so another example, e to the z cosine 2z plus 1. So, you know, it all goes back to trigonometry, basically. What I'm saying is most of the examples that I would want you to do, they involve like just using trigonometry. And this one, I use the adding angles formula, right, to expand the cosine like so, and then substitution. And then what do? After I've got the, you know, the series out here, I then do what? I just use the Cauchy product. I just multiply term by term, and there you go. That's the first three terms in the Laurent series, if you will, or the power series for e to the z cosine 2z plus 1 centered at 0. Let's look at another example. This one, if we multiply 1 plus z squared plus times 1 minus z plus z squared, this is actually, well, I mean, this one's kind of a stupid calculation. So what I did was I converted this to what it converges to. What does this converge to? This is, you know, plus minus. This is 1 over 1 plus z, right? So you multiply these. That's 1 over 1 minus z squared, which gives us that. Of course, if you were to just do the Cauchy product to get straight from here to here, you'd also get the same thing. So I'm just sharing with you some sort of calculational ideas, all right? What's next here is I ask the question, given a series, suppose you want to look at the reciprocal of the series, all right? What are the coefficients for the reciprocal series? So the reciprocal series, let's say 1 over this, I'm going to say is equal to bk times that. The question is, what are the bk's given the ak's, right? Well, this times that has to give me 1. So if you look at the Cauchy products, you got to be able to solve them order by order, right? So first of all, b sub 0 has to be 1 over a sub 0. And you can solve this for b1. You can solve this for b2. I mean, and you can just go up the chain. So if you've got that at least a sub 0 is non-zero, you can reciprocate the series. The series has a reciprocal only if the leading coefficient is non-zero, is what we're seeing from these equations. So I actually suffered through it here. I used my reciprocal equations to find that this is like 1/2 plus z plus ... I don't really recommend this as a method of calculation. I'm just messing around, all right? The standard way to find the reciprocal of a series is with long division. So here's an example of long division. We can divide this into that. That ends up being the remainder at this point. So let's see here. What I get is that sine z divided by cosine z I tell you. So there's the series for tangent obtained by dividing the sine series by the cosine series. There's the first few terms. So division of series, it's not something that, you know, I take lightly. I think that takes some practice to really get good at it. Here's 1 over cosine z, right? This is yet another calculational technique. If I've got the leading coefficient as 1, I think of this in terms of being a geometric series, right? So 1, that's my r, so this is 1 plus r squared. That might make sense as a calculational technique. There's a lot of different ways to look at reciprocating a series. There's just a couple for you. And that brings us to the next section here. So if you guys have questions about this section, you know, feel free to ask them at the start of next class or something, okay? I will shut up.